Welcome back, folks. We're talking about BJTs for the first time in this class. What I want to look at now is what I want to do is a deeper dive into the volt-amp characteristics. We need to use these to do analysis on these circuits at some points, but we got to get real comfortable with how they're displayed and how we calculate them, given that they're like these crazy nonlinear functions that make things a little sloppy for us, but we can deal with it. We got the tools, and I'm going to introduce those over the next few videos, but let's just look at the VI characteristics for the BJT transistor. Okay, so really what we're after here is, there we go. How do we calculate the collector current? So that's the current flowing into the collector. And we calculate that based off of the current flowing through the base and the voltage across the collector emitter terminals. Okay, so it's three-dimensional. The diode was two-dimensional, so we could plot that really nicely on a plot. But now we're using an additional variable, so we have to add an axis to that plot, and it ends up being three-dimensional. The nonlinear function that we're plotting is right now just for the active region, which is one of the four regions that we can discuss. Three are a little more common, but there's a fourth as well. And it looks like this. Okay, so we have the collector current, and we have some parameters. Let me scroll up on this. We have some parameters of the device. We can go dig these out of data sheets if we need to, or LT-SPICE models if we're doing that. But there's some similarities with the diode, and well, frankly, of course there are, because it's a bunch of PN junctions. It's two PN junctions smacked together. So we have the saturation current, okay, as a parameter of the model, and then we have this natural exponential. Rather than the voltage across the diode from anode to cathode, now we have the voltage from base to emitter. Okay, so we have down here VBE, the voltage at the base. WRT is with respect to the emitter. That's what's going to dictate how much current's flowing through there. Over here we have another phenomena. You'll see that the curves aren't flat at the top, and that's due to something called the Early voltage. And Early was named after James Early. He was one of the early guys studying semiconductors. So VA is another parameter of the transistor, and that kind of correction factor for the collector current is dependent on the collector emitter voltage. So we have the voltage at the collector with respect to the emitter. Okay, so some of these things are parameters, some of them are the independent variables that we're plotting against. Now, plotting this function, since it's three-dimensional, isn't really data sheet friendly. It's not something that I could stick on a piece of paper and have it be entirely clear. And certainly if you go back to the 1940s when we were first, not we, the collective we, were first looking at transistors, visualizing three-dimensional functions wasn't that easy. So what we ended up with was curves that were plotted that look like that. You might have seen something like that. If you look at the front of your textbook, that curve is important enough that became the picture on the front of your textbook. And it's really meant to be a three-dimensional curve, but it's not always clear. Okay, so we have these multiple curves going up like this, but what does that really mean in terms of calculating the collector current based off of the base emitter voltage and the collector emitter voltage? Okay, so so let's see what that looks like. I plotted something for you. I got some MATLAB running here. Let me get it up and plot it. So I took this function and I plotted it. I plotted over a set of values for the two things going in to the function, okay, base current and collector emitter voltage. And it looks something like this. Okay, so if I want to find a collector current, I can find the corresponding base current along this axis, and I can find the corresponding collector current off this axis, and there's going to be some point on this curve. Okay, and that's going to tell me the collector current. So we can, it's nice and three-dimensional. We can rotate it around, and this is really the volt-amp characteristic we're dealing with. It's no longer just a nice two-dimensional thing, it's three-dimensional. All right, but to get from this three-dimensional reality that's based off of the equation that's hiding behind right here, like that equation is what I used to plot this, down to this, we flatten it, okay? And we flatten it along one of the axes, and the axes that it gets flattened across most commonly, that gave us this type of set of curves down here, is IB, okay? Each one of these traces is a slice of the IB curve, and we see those traces along here, okay? Those lines right there, I'm hoping you can see that cursor moving, okay? That's one of those slices that we see here. And the way it ends up working is if we rotate it this way and kind of flatten it out. Okay, I'll try to get it as, oop, that's perfect, as flat as we can. Okay, and now we see each of those slices that look like this from that three-dimensional curve. Okay, each one of those is a value of IB. It doesn't mean that we're stuck with that. It doesn't mean that that's the only value of IB we can. It just means that that's where we chose to plot it, and we kind of have to visually interpolate what's going on when we're in between those. Okay, so let's see. Let's take this curve, because I think that's worth having in your notes. Right? That's your volt-amp characteristic for a BJT, and it looks something like that. Ooh, I'm running out of room here. It's a little snug, Okay, I think that's good enough to get them next to each other like that, and then we rotate it as I mentioned. Okay, like that. I'm going to run a little piece of code over here to rotate it the way I want it to, and we end up with an equivalent. Set of curves. Okay, so let's say it looks like that, and each of these lines, I'll do my best to trace them here, is a value of constant IB. Oh, that's a mediocre tracing job. I'm getting used to using the stylus again. Okay, so if we wanted to figure these out, if we were making our data sheet and maybe we recorded this data from an actual transistor, which there are devices to do this with an actual transistor. They're called curve tracers. Okay, all they do is vary IB and vary VCE and then take measurements and draw them on a screen. Okay, each one of those red lines, corresponds to one of these traces. So if I want to figure out what they are, I can just rotate it that way, and we can see each of those lines. So this looks like it's about 30 microamps, 25 microamps, 20 microamps, all the way down. Okay, so in the data sheet you'll usually see 30 microamps, 25 microamps. Okay, and this all refers to the value of IB: 20, 15, 10, and 5. Okay, so visually that's what's going on. It's a three-dimensional function. It's based on this expression, but we can't pull values off of this very easily in a data sheet, so instead we flatten it and we draw some curves. Okay, we got to figure out how we're going to use this in analysis, and that's really the tricky bit, is how do we handle this? Okay, and we can use that nonlinear function. We did that with a diode. You had a problem on the homework that you're working on right now, where we used the nonlinear function to find the exact value, and that was good, but it was also intractable as the problem gets more complex. If the circuit has a lot of parts, we can run into some trouble. Okay, so how do we deal with this nonlinearity? How do we deal with this nonlinearity when performing analysis? Okay, nonlinearity. And we have some options. Performing analysis. All right, so that's the question. And our options. What are our options? We could do what we did with the diode. We could use MATLAB or something similar, okay, to solve that nonlinear system of equations. From your previous classes, you may have run into something called load lines, okay, where you figure out what the extremes are and you solve it graphically. And I think there was one on the image up here. Right, that red line is the load line, and you can say, okay, where do they overlap? Okay, and that's a graphical way to solve a nonlinear system of equations. But, you know, again, what if the circuit is really complex? What do we do? There's some approximations we can make, and they're pretty good. So just like we did with the diode, we can start to figure out some linear approximations that will allow us to apply mesh, nodal, so forth. Okay, all of our structured methods of analysis. You can do seat of the pants. Your textbook uses seat of the pants. Most textbooks do, and they're just silly, if you ask me. We want to have some kind of structured approach to circuit analysis. Okay, so this is what we're going to do over the next few videos. We're going to start looking at what are these linear approximations that allow us to perform analysis on circuits that have BJTs in them. And that's what we want to do. Okay? Stay tuned and good luck.